So the data for today's session is uploaded in the chat. So this is the data we are going to use. The description of the data is this. The problem statement is also given here. We have to predict. There are two dependent variables, so we have to use the same independent variables for predicting the two sets of dependent variables. So whether the respondent has taken H1N1 flu vaccine, whether the respondent has received seasonal flu vaccine. That is the one. And 0 means no, 1 means yes across the variables. So we have these set of variables which are there in our data. You can see the data here. So we will work on this data and try to go through our concepts. So let's import the library, import pandas as PD, import numpy as NP, import matplotlib.pyplot as CLT, and percentage matplotlib inline. So the mandatory libraries which we need, we are importing. And I'm setting up my working directory folder. So import IO and percentage CD in double quotes. We have to paste the folder path where the data is stored. So the folder path, copy. Paste it in the double quotes and shift enter. The path has been set. So the folder has been set as the working directory. The folder has been set as the working directory. Now we can use this folder for, you just need to put your data into this folder and we can directly call it by the name. So let us import the data. X underscore train is equal to cd dot read underscore csv, open bracket, double quotes. The name of the file is train underscore set underscore feature. Train underscore set underscore feature dot csv. error. What is this error? I think the folder path is not completely set. Let me just set the path. Prediction. Oh, training. What? It's not train. Training. So we are importing the session. We are importing the train data labels, and also y underscore labels. Y underscore labels is equal to cd dot read underscore csv. cd dot read underscore csv. The name of the variable is training underscore set underscore labels. Dot csv. So the data is there. I'm again pasting the data link here. The driven data link. There in the data is there. Anybody needs any data help? You can tell me. That data is there already in the chat window. So once all of you are confirmed that you have imported the data, can you please confirm so that I can go ahead?
Yes, sir.
So actually, there are two sets of dependent variables, and the same set of independent variables will be used for studying the dependent variables. So one set of independent variables to study two sets of dependent variables. So we have to build basically two different models. So if you look at the dependent variables, it's under x underscore train. Dot head. So we have various variables which are there in the data. Let me make it 3 lines only so that everybody can see it clearly. We have 36 variables including the respondent ID. So H1N1 concern, H1N1 knowledge, behavioral antiviral meds, behavioral avoidance, behavioral face mask, behavior wash at hands, large gathering. So there are a lot of variables which are there, both numerical as well as categorical. And then we have some variables like employment occupation and employment industry also, where we have certain amount of missing values. So the brief understanding of this data is this. The data dictionary is given. So there are behavioral variables. If you are looking at the problem description, there are behavioral variables. There are variables related to doctor recommendation. There are variables related to health insurance, the opinion variables. We have a lot of opinion variables also, where respondents' opinions are taken based on the H1N1 vaccine effectiveness and all, right from highly effective to not at all effective to very effective. And then we have the age group, education, the demographics of their employment and employment occupation. So this data has a comprehensive variable wherein we are looking at what we call opinion variables as well as behavioral variables. We have both the opinion variables and the behavioral variables. And then we have to use these set of variables to predict the dependent variable, which is there in our data. That there are two dependent variables, seasonal flu vaccination and H1N1 flu vaccination. Okay, so this is the brief introduction of our data. If all of you have imported the data, I think we can go ahead and check for the missing values. All of you have imported the data. Can you guys please confirm? So we have imported the data. Now let us look at our data. So X underscore train dot D types, data types. So what are the data types we have? Most of the data types are float 64. But they are not cannot be treated as numerical variables. They have to be treated as categorical variables. So we have all the variables in the data as float 64. So, but can we treat them as numerical variables? No, because they are all like a scale type of data, and we have object variables also, wherein we have the object data. So this is the B type we have in our variable, in our data, both float, in64, and object. All types of data are there in the data. So X underscore string dot shape. So if you look at our shape, we have 36 variables and 26,707 observations. We have 36 variables and 26,707 observations. So this is the data we have, 26,700 rows, 36 variables or 36 columns. So we have this set of data. So we will be using this data, independent variables, to predict the dependent variables. Now, data pre-processing is a very important task here. We need to check whether the data is in a correct shape or not. So we need to look at the pre-processing. There are a lot of tasks in the pre-processing. We will be working on those pre-processing tasks to understand how we have to run a lot of data pre-processing tasks in this data. If you look at a lot of, like one of the most important data pre-processing tasks is missing values. Missing values imputation. So missing values imputation, x underscore train dot is null dot sum dot sort underscore values ascending is equal to false. So we have a lot of missing values in employment, occupation, industry, health insurance, income, poverty. So we have missing values in many columns. So employment, occupation, employment, industry, health insurance, income, poverty, doctor recommendations. So we have missing values in the data. Most of these missing values, almost all columns are missing values. Almost all columns have missing values. So we have to treat these missing values. This is the biggest challenge we have in data science, how we treat these missing values. So if you look at the missing value treatment, we will look at each variable and then do it manually. There are multiple methods. Manual method of missing value imputation can be done. And also you can use algorithms like KN and Imputer to do the missing value imputation. So there are multiple ways of doing this missing value imputation. You can do it individually using the columns, or you can do them using an algorithm like KN and Imputer will be used to fill the missing values in this data. So we will be using a missing value algorithm called KN and Imputer based on k-nearest neighbors algorithm that will impute these values. KN and Imputer will impute these variables, and then so k-nearest neighbors algorithm is one of the algorithms which uses a distance metric. The closest distance neighbors will be used for imputation. So it is a very interesting algorithm which is widely used in missing value imputation. So if you look at this data, we need to understand that most of this data which we are dealing with is categorical in nature, but the data type is showing as numeric, but we have to treat them as categorical variables. We have to treat them as categorical variables. So employment, occupation, employment, industry, health insurance, income, poverty. So these are all your categorical data as per the data statement. If you look at the problem description, they are all either binary variables or they are object variables. Binary variables or the opinion variables are all Likert-Scale variables. Opinion variables are all Likert-Scale variables, and behavioral variables are all binary variables. And even if you look at the H1N1 concern and H1N1 knowledge, that is also typical Likert-Scale type variable, but it is not a Likert-Scale variable. So we have to fill up these missing values before we proceed to do any type of analysis on this data. So the manual imputation model is very easy to run, where we can impute them with the most frequent value, and then we can do it by using that value, or we can do using the what we call the algorithm-based value. Yes, you will get it. So let us split data into numeric columns and object columns. Let us split the data into numeric columns and object columns. Numeric columns numeric call is equal to x underscore train dot select underscore d types include is equal to np dot number. Object call is equal to x underscore train dot select underscore d types include is equal to square bracket single quote object. Now np dot number will take both numeric as well as float as well as int64 data. Numeric variables will take both float 64 and int64 data. And it will combine them into one type of variable under the category called number. So if you print the shape, print numeric calls dot shape, print object calls dot shape. So we have 24 numeric calls and 12 object calls, which are needed to be which are there in our data. 24 numeric calls and 12 object calls. So if you look at this data numeric calls, we need to separate the category calls from the numeric calls. We need to separate the category calls from the numeric calls. So if I run numeric calls dot column, you can see here almost all of them are binary variables, except household adult and household children. So except household adult and household children, rest of all are binary variables, or what we call like a scale type of variables, like H1N1 concern and H1N1 knowledge. So we need to separate these numeric columns into category columns. From these numeric columns, we need to separate the categorical variables. Now, let us separate the categorical calls from the numeric calls. So, in this whole set of numeric calls, the only calls that are numerical in nature are household adults and household children. How many adults are there and how many children are there? Those are the numeric data which we can take. Rest of all are categorical calls. So what we can do is categorical call is equal to numeric calls dot drop open bracket single quote and household children, household adults, comma, axis is equal to 1. So we have dropped the columns from the numeric calls, and we have named it as categorical calls. Oh, sorry, I'll name it as categorical calls. Let me then I named it wrong, so I'm just correcting my name error. So categorical calls we have separated from the numeric calls, and now we will get our numeric calls, which are your is equal to numeric calls double square bracket. You can copy these two variable names. Double square bracket is for selection of two variables, and then we will get the variables as category calls, numeric calls, and object calls. The three types of data we have in our data. So I can add one more column variable here. Print category calls dot shape. So 12 object calls, 2 numeric calls, 22 categorical calls. So we have these set of calls in our data which we need to pre-process. Pre-processing means converting them into dummy variables, missing value imputations, and all those things have to be done. So we have split the data into 3 categories. All right, all of you have split the data. Yeah. So let us start with the missing value treatment. Missing value imputation using KNN imputer. So the KNN imputer uses K nearest neighbors algorithm, which is a non-parametric algorithm. It is a non-parametric algorithm. So when I say non-parametric means there are no underlying assumptions. There are no underlying assumptions for the data. For data, there are no underlying assumptions. So if you take parametric algorithms like multiple linear regression, there are many types of assumptions which you need to make. Like the data must be closer to normal distribution. So there are a lot of what you call assumptions within the parametric algorithm. So whereas in non-parametric algorithm, there are no underlying assumptions. So KNN uses the memory storage method wherein it calculates distances and store them in memory and use them as and when a new observation needs to be categorized. A new observation needs to be categorized. That time, it uses that memory input. So KNN algorithm uses the memory storage method wherein it uses the underlying assumptions for data. It uses the where it initially calculates these distances and stores them in the memory, and as and when required, recalls this memory and uses that for imputation of data. So the KNN imputer in Python, sklearn sklearn impute, we have this KNN imputer with the default n underscore neighbor is equal to 5. So it uses the nearest 5 neighbors data tracking trend and pattern and imputes the value with that data trend and pattern. So the KNN algorithm, the sklearn Python, it uses the nearest 5 neighbors. You can change it if you want. You can change it to 8 neighbors or 3 neighbors, your choice. But by default, it is 5 neighbors. The 5 neighbors will be utilized to impute the missing value in the data. So that is what this sklearn KNN imputer is all about. So the sklearn KNN imputer is a very interesting imputer which is used to read the missing values. This is the function syntax of the you can see the missing values are nan underscore neighbors is equal to 5, weight is equal to uniform, metric is to nan underscore equivalent, copy indicator, and it uses this for understanding the value. Yes, somebody has a doubt, you can ask me. Yes. So add underscore indicator, we can use value metric is Euclidean uniform value and underscore Euclidean. So we can use KNN imputer for running the missing value.
Sir, I have a question. You said that it calculates the distance, but since its own value for the particular feature is missing, then what is the reference? I mean, how it is calculating the distance?
Nearest 5 rows.
Okay, nearest 5 rows.
Yeah.
In the data set, no?
Yeah.
Sequentially.
Sequentially, yes.
Okay, got it, sir. Thank you.
So we will run this on our data. Let us do it on category calls first, and then we will do it on numeric calls also. And then in the end, we will do it on object calls. So from sklearn dot impute import KNN imputer. From sklearn dot import KNN imputer. Imputer is equal to KNN imputer. We will take the default neighbors as 5. Let us impute with the default imputers as 5. Okay. Now, category calls imp is equal to imputer dot fit underscore transform category calls. category calls imp is equal to imp dot imputer dot fit underscore transform category calls. So it will impute all the categorical calls that have missing values with the closest neighbor or with the nearest neighbors. It uses the nearest neighbors to impute. So KNN imputer is a very one of the robust algorithm for missing value treatment. We have other algorithms also wherein we can use algorithms like what you call mice, multivariate imputation, missing imputation is in chained equations. Mice is being implemented in Python. It is in the beta version. It is now called as iterative imputer. It is in experimental stage. Maybe in the next version of sklearn, we will get the mice imputer also working here. So the category calls have been imputed. Similarly, numeric calls imp is equal to imputer dot fit underscore transform numeric calls. So we are imputing the numeric calls. If there are any missing values, they will also be imputed. Now, for imputing the missing values in object calls, it is a little bit complicated. We need to initially run a label encoder because the KNN imputer needs data in numeric format. So we need to first label encode the object data. And label encoding object data is not straightforward because if there are missing values in data, label encoder will not run. So we need to write a small function loop wherein the label encoder will encode all the observations which are not missing and leave the observations of missing as it is as np.nan so that we can run the KNN imputer on that data and we will get the imputed values. So that is the methodology we need to follow for KNN imputer. So KNN imputer uses the numerical data type. So if you are looking at imputing object columns, first we need to label encode them. We need to label encode them. So let us call the function from sklearn dot preprocessing import label encoder. So label encoder will generate numerical IDs in alphabetical order for the various categorical levels in that particular data. For various object levels, it will create numerical IDs. It will create dummy numerical IDs.
Sir, a doubt, sir.
Yeah.
Sir, it is what is this label and encoder, sir? What is its
Copy variable encoding.
role?
It will convert text to numbers. It will convert text to numbers by assigning numerical codes. So string calls is equal to object calls dot as type str string dot apply lambda anonymous function series equals to pd dot series open bracket and press enter label encoder dot fit underscore transform So what we are trying to do is we are trying to convert our data from data frame into a PD series so that we can run the label encoder series square bracket series dot not null, series dot not null, series dot not null, come out of the round bracket after the square bracket, comma, index is equal to series square bracket series dot not null dot index. So what this will do is it will first convert the object calls into a string type, then it will apply a function called pd.series where it will convert the data into series, and then it will implement a label encoder on that series. It will only consider those cells which are not null. Not null means which are not NA, and then it will index the series accordingly with the index. So this is what it will do. So it will label encode the remaining variables, and it will leave the missing value variables untouched. It will label encode other variables, and it will leave the missing value variables untouched. Now we can impute our missing values. So in 28, first we are converting the data into a string. We are actually the data is string only, but still we are re-informing it as string. Then we are converting the data into a series for fitting a label encoder. Label encoder will convert the text levels or object levels into dummy variable encodes, and we are telling the label encoder to run only on those cells which are not null. If the cells are null, do not run label encoder on those cells. We are looking at cells which are not null, and then it will label encode the rest of the cells. That is what this thing, the whole process is doing. So it will convert the data. If you look at string, let me just show you the output. pd.dataframe string calls dot head 2. See, it converted everything into numbers. It converted everything to numbers. It has converted everything to numbers. Okay, whereas our original data is object calls dot head is text. Our object calls dot head is text, which has been converted into numeric data by using the label encoder. Now we will impute the string calls. String calls imp is equal to imputer dot fit underscore transform string calls. So it will impute the missing values in the string calls. So we have imputed the values of all the three categoricals, numericals, and string calls. Okay. Now we need to dummy encode the categorical calls and string calls. Now there is a change in this thing. Earlier we were using label encoder for encoding the dummy variables. Now that thing has changed. Do not use label encoder on independent variables, do not use label encoder on independent variables rather you should use pd dot get dummies, pd dot get dummies or one hot encoder must be used on independent variables. On independent variables, do not use label encoder, use get dummies or one hot encoder. Label encoder must only be used on dependent variables. Label encoder must only be used on dependent variables. So this is one of the important changes. Earlier we were using label encoder for dummy variable encoding, but in the last version of sklearn they have changed it. We have to either use get dummies or label encoder or one hot encoder for dummy encoding, dummy variable encoding. So this is one thing you need to understand. So please do not use label encoder on independent variables. So categorical calls dummy is equal to pd dot get underscore dummies category calls. Now print category calls dot shape and print category calls dummy dot shape. Oh, why did dummy didn't work? We need to convert them. Dummy will create new columns. PD get dummy will create new columns. So that is one thing we need to understand. The shape of the dummy variable column has to be more than the thing. So it PD get dummies, it didn't run on the category call. Why? So let me just check the code of the PD get dummies. I missed something. PD dot get underscore dummies. So we have to prefix none, prefix separator, dummy NA false, columns none, drop underscore false, D type is equal to none. Okay, PD dot get dummies, MP dot man. D type is float we have to add. I think we have to add D type is equal to float. Comma, D type is equal to float. Yeah, let us do this. Oh, still not working. Oh, I missed somewhere. 1 second. Let me just check. Where did I do the H1 and 1 vaccination? Correct? Then it also creates now. So we have used ordinal encoder. Rather than get dummies, we have used ordinal encoder. Let us look at this ordinal encoder. So what we can do is ordinal encoder encode categorical features as an integer array. So the input is array like integers or strings denoting the values taken on by categorical features. So we will use ordinal encoder for this process rather than get dummies. Or we can also run get dummies. Get dummies will add more columns to the data. So get dummies, we can also add more columns to the data for float. So what happens here is no. Dummies will work on numerical data also. Okay, we have to give the data type as dot type str. So we will use get dummies or we will use ordinal encoder. One second. Let me just check the data type. Categorical calls dot d types. So the d types are all float 64 except the int 64. Okay. So if we remove the int, then I think the dummies will work. Categorical dummy dot head. For float type columns, how we can do it? Or we will use ordinal encoder. That would be the better option for doing this. I'll also give you the type. So from sklearn dot preprocessing import ordinal encoder. From sklearn dot preprocessing import ordinal encoder. OE is equal to ordinal encoder. So cat calls encode is equal to category calls dot apply OE dot fit underscore transform. Oh, we got an error. Oh, we have to give it the other way around. Apply will not work. So OE dot fit underscore transform category calls. Oh, what happened? Oh, T type float 64. There are too many big values are there. So ordinal encoder is not working. Why? Worked earlier without any problem. Okay. All right. So ordinal encoder is giving us an infinity error. Input contains nan, infinity, or a value large, too large for T-type float. But nans are not there. Nans are there. Category calls. Oh, I have to use the imp data. Sorry, I am using wrong data here. So that is my mistake. Sorry. I have to use the imputed data, right? Cat calls encode is equal to OE dot fit underscore transform cat calls category calls imputed category calls. So I was using earlier non-imputed one. Similarly, string calls encode is equal to OE dot fit underscore transform string calls imp. String calls imp. Okay, so we are running an ordinal encoder. Okay, we can do ordinal encoder like this, where we have the number of columns restricted to the original columns. So the shape will not change. But if you want to, if you look at this, the whole context, print cat calls encode dot shape. Sorry, print is small letter. Print string calls encode dot shape. So the number of columns will not increase. The number of columns will be the same. So the number of columns has not increased here. They will remain same. But if you use a get dummies, it will add more columns to the data like this. So what we call cat calls dummy is equal to pd dot get underscore dummies category calls in dot as type str. Categorical calls in dot as type str. Data must be one dimensional. Okay. Let me check the shape of category calls in dot head. Category calls in dot head. It's a numpy array. It's a numpy array. So we need to convert into a data frame. Then only we can run PD get dummies. So that was the error. So let us do that. Cat calls dummy is equal to PD dot data frame category calls imp. Cat calls dummy is equal to PD dot data frame cat calls imp. Cat calls dummy is equal to PD dot get underscore dummies cat calls dummy. Let me print the shape. Did it change? Cat calls dummy dot shape. No, 22 only. So we have to change this as dot as type str. Dot as type string is int. See, oh, it has created many columns for 26,903 columns. How did it create? Oh, this is completely created a different type of set. So this is wrong actually. This is not the correct way. The classes have to be string, but I think it is taking each of them as string. So this is not the right way. This is not the one we should go with. Let us go with encode only. Let me see if I can get the get dummies by end of the session. How I encoded using the numerical data. Because the float data, if it is there, then we need to, because it is not running on the float data. It is not running on the float data. It is running on the categorical data. So let me just give you that part of also. Okay, we'll work on it. Like no problem. Let's go ahead. So we have done the ordinal encoder. Okay, now we will convert our data. X underscore train df is equal to cd dot concat open bracket numeric calls in comma cat calls encode comma string calls encode comma axis is equal to 1. So what happened? Okay. So we have to convert them each into cd dot data frame numeric calls in comma columns is equal to numeric calls dot columns. Then we will do td dot data frame category calls encode comma columns is equal to category calls dot columns, so a comma pd dot data frame string calls encode comma columns is equal to object calls dot columns close bracket, and then we will convert them into a data frame. So because they are numpy arrays, we cannot concat them into one single data frame. By converting them into a data frame, we can concat them. So x underscore train df dot shape. So we have 36 variables of 26 and 26,707 observations. So this is the process of converting the numpy arrays into data frame and retaining the column header. All right, all of you got this data to this structure. Okay, all of you once you're done, please confirm. All right, can I proceed? Okay, so once we have done the encoding process, we are ready to run our algorithms. We are ready to run our algorithms. Okay, now y is equal to y underscore labels dot seasonal underscore vaccine, y dot value underscore counts. So we have 14,272 people who have not taken vaccine, 12,435 people who have taken vaccine. So this is our seasonal vaccine This is the related to seasonal vaccine. Now, if you see the observation classification, there is no imbalance in the data. Both the classes are equally represented. If you closely watch the data, there is no data imbalance. Both the classes are equally represented, right? So that this is not a imbalanced data, this is a balanced data. So on a balanced data, we can run a classification model and then see how the performance metrics we get on that one, right? So since the data is binary variable, we can implement what we call a logistic regression. So since the dependent variable is binary, we can do classification model. We can do the classification model. Since the dependent variable is binary, we can do classification models. Now, from sklearn dot linear underscore model import logistic regression. From sklearn dot linear underscore model import logistic regression. Logic is equal to logistic regression, null braces. Before that, we have to x underscore train df is equal to x underscore train df dot drop. We have to drop the respondent ID, which are unique IDs. Respondent ID is there, right? So we will drop the respondent ID. So respondent underscore ID is there, which is of unique IDs, which we don't respondent underscore ID, comma, axis is equal to 1. So I have dropped the respondent ID. Now we are ready to meet the model. Logit model is equal to logit dot fit x underscore train df, comma, y. Oh, so we got a convergence warning. It says total number of iterations reached limit. So it is giving two solutions: increase the number of iterations or scale the data. At this point of time, scaling the data is not possible. Already most of the variables are binary. So we will increase the iterations. Max underscore iteration is equal to 5000. Oh, sorry. I re-clicked this. Sorry. So it has fitted the model. Logic model dot score x underscore train df, comma, y. So we got an accuracy of 77.4. We got an accuracy of 77.44. 0.774, we got the accuracy. Now we can predict also. Logit predict is equal to logit model dot predict x underscore train df. So we have predicted the model. I have deleted the respondent ID. Let me just run this line one more time so that you guys don't have any doubt in the notebook later. We have predicted the logistic model. So we have built the logistic with 5,000 iterations, and we have also predicted it. Now I am doing the confusion matrix. PD dot cross tab y comma logit predict. This is the confusion matrix which we got. This is the confusion matrix which was built based on the logistic regression on seasonal flow. Confusion matrix for seasonal underscore flu vaccine. So this is the confusion matrix which I created for seasonal underscore flu vaccine. All right. So we have built a model, and then we have scored the model. The score is nothing but the accuracy, which is calculated from the confusion matrix. The score is the accuracy calculated from the confusion matrix, and this is the confusion matrix. To confirm, you can add the diagonal one. 11,551 plus 9131 divided by 11,551 plus 2721 plus 3304 plus 9131. So you get the same 77.4 accuracy, which you can see here as part of the score. Now, when you look at these things, we can't only go with the accuracy. We also need to understand the other metrics. The other metrics are also very important here. So from sklearn dot metrics import classification report, comma, plot underscore ROC underscore curve. So we will print the other metrics also, because we can't only go with accuracy. We need to look at the other confusion metrics also, which were there. Now, what are these other confusion metrics? There are a lot of metrics that can be calculated from the confusion matrix. Okay. So for you, just to recap, these are the different metrics which we calculate from a typical confusion matrix. This is the metrics we do. We calculate the sensitivity, we calculate specificity, we calculate sensitivity, we calculate specificity, we calculate precision, we calculate the negative value rate, and we also calculate accuracy. So sensitivity is how many positives are classified as positives, specificity how many negatives classified as negatives, and precision will tell us overall how many positives are there classified as positive in our data. So these are various metrics: sensitivity, specificity, precision. Sensitivity is also called as recall. Sensitivity is also called as recall. That is also very important. So these metrics can be printed using the classification report. So print classification report in bracket y comma logic predict. For logic predict, we can see here the overall accuracy is 77. The precision, recall, and F1 scores are very important here. All of them are closer. For a balanced data, the precision, recall, and F1 score. Now, F1 score is again a metric calculated using precision and recall, are closer for both classes. For both classes, they are closer. Now, F1 score is again a metric which is used in classification these days. The formula is again based on confusion matrix only. It is F1 score is 2 into precision into recall divided by precision plus recall. 2 into precision into recall divided by precision plus recall. That is the formula of F1 score. So let me see where I can get you the exact formula for F1 score. Yeah. So this is the formula for F1 score. Oh, it went to YouTube. Sorry. I don't want to use YouTube things, but this is 2 into precision, or we can see here only. Here only. Weighted average. F1 score is 2 into precision into recall divided by precision plus recall. It is a weighted average of sensitivity and precision. It is a weighted average of sensitivity and precision. Higher F1 score, the better. Higher F1 score is the better one. So if you see here in our data, all the metrics are performing very, very close to one another. All the metrics are performing very, very close to one another. Okay. So based on this, we can also plot the ROC curve. Plot ROC curve, the model name logic, comma, x underscore train df, comma, y. Now the AUC or area under the curve is 85%. AUC is 0.85%. The area under the curve, you can see here, it is in the metric only 0.85. So the classification report and the ROC curve are giving certain amount of accuracy to our logistic regression, which is your base model. Which is your base model.
Sir, can you explain how to look at this ROC curve?
So in case of ROC curve, we look at the AUC. The AUC is the most important metric. The higher the AUC, the better. The higher the AUC, the better. So if you look at the AUC, see here. AUC of 0.5 is unsatisfactory. AUC of 0.6 to 0.7 is satisfactory. AUC of 0.7 to 0.8 is good. And the AUC of 0.8 to 0.9 is very good. And the 0.9 to 1 is excellent. So our AUC is falling in the category of very good. So as long as the AUC is above 0.6, you can say that your model is good. So these are the metrics you need to refer for AUC. So AUC above 0.6 till 0.7 is satisfactory model. 0.7 to 0.8 is good model. 0.8 to 0.9 is very good model. 0.9 to 1 is excellent model. So these are the metrics which we generally use when we do the AUC for classification problems. For classification problems, when we do the area under the curve, we can see this AUC metrics. Now, is it clear how to interpret the AUC metric?
Yes, sir. Thank you.
So AUC curve we got is 0.85. For a binary logistic regression on this data, for a balanced data, we got 77 as accuracy and AUC of 0.85. And I want you to look at this very closely, the precision and recall score for 0 class and 1 class. In our data, in this data, 0 and 1 are almost equal. In this data, 0 and 1 are balanced, they are equally represented. So you are getting these scores in a very, very closure. See, 0.78, 0.77, 0.81, 0.73, 0.79, and 0.75. The class representation is 14,272 for 0, 1,2435 for 1. So this is the context of the balanced data for logistic regression. Okay, all of you got this?
Yes, sir.
Yeah. Now, so we have done the missing values and we have built a model on a balanced data. Now, let us focus on the second important topic we are discussing today, imbalanced data. The imbalanced data, particularly in classification problems, is a big issue. Classification problem or classification model is an issue. Now, why will be H1N1 vaccine? We will take Y as our H1N1 vaccine. In the earlier case, our Y was seasonal vaccine. In this case, I am changing my Y. Y means our dependent variable. I am changing my dependent variable from seasonal vaccine to H1N1 vaccine. The independent variables will remain the same. The independent variables will remain the same. The same set of independent variables which we are used to predict the seasonal vaccination, seasonal flu vaccination will be the same. Okay, we will use the same. So Y is equal to Y underscore labels dot H1 H1N1 vaccine. One second, I think the name it's not taking, sorry. Y underscore labels dot head. Oh, H1N1 is head small letter, okay. Y is equal to Y underscore labels dot H1N1 vaccine. So here I am changing my dependent variable from seasonal flu vaccination to H1N1 vaccine. Now I'll print the value counts. Y dot value underscore counts, the frequency counts of the classes. Now you can see here, this is a classic example of imbalanced data. This is the classic example of imbalanced data, where H1N1 vaccine no, H1N1 underscore vaccine 0 means no, H1N1 underscore vax comma 1 is yes. So there are very few people who have taken H1N1 vaccine. Lot of people have not taken H1N1 vaccine. Whereas in case of our seasonal flu, this is not the case. In the case of our seasonal flu vaccination, we can see here, people who didn't take the vaccination are 14,272. People have taken vaccine is 12,435. There is no majority representation or skewness towards one large class here. Both are almost equally represented. But if you go down and see our H1N1 vaccination, you can see here there is a clear imbalance in our data. 0 is majorly represented and 1 is less represented. So classification models are biased to majority class, are biased towards majority class. Majority class in dependent variable. So in a dependent variable, if there is a majority class, then the classification models have a natural bias towards those majority class. So when you have data in this situation, a balancing has to be done. Imbalanced data has to be balanced, before we run any classification model. Before we run any classification model, this data has to be balanced. Okay, so now if we don't balance, what will happen? Now let me logic model underscore imbalance data is equal to logit dot fit x underscore train df comma y. As I told you, y has changed. The independent variables remain the same. I am building a logistic regression model. I have built a logistic regression model on this data. On this data, I have built a logistic regression model. Okay. Now, logit model underscore imbalance dot score x underscore train df comma y. Now the accuracy is there. Accuracy is 83.4. Now the accuracy is very, very good. The accuracy is far better than our seasonal flu. Accuracy of 83. Whereas for seasonal flu, we got an accuracy of only 77.44. So here the accuracy is very good. But if I print the classification report, so imbalance predict is equal to logit model imbalance dot predict in bracket x underscore train df. So I have predicted on the imbalanced data. Now I'll print the classification report. Print classification underscore report y comma imbalance predict. Now look at the classification report closely. The precision for majority class is 0.86, recall is 0.95, F1 score is 0.90. For the minority class, look at the minority class 0.68, 0.42, 0.52. So this is what happens in imbalanced data. In imbalanced data, accuracy is not the right metric. See, accuracy is 83%. For imbalanced data, accuracy is not the right metric. So we always have to look at the other metrics when you're looking at your imbalanced data. Obviously, there will be imbalance in your data because the negative classes are always minimal. Be it as credit card fraud, be it a loan default, very few people will do it, right? So not more people will do it, very few people will do it. So always there will be less number of cases. But classification models by nature have a bias towards the what we call larger class. And you can see it here. For one, the precision is very less, recall is very less, and F1 score is also very, very less. So this is the problem of imbalanced data. This is the problem of imbalanced data which we see in data science. Now, when you have this imbalanced data, you need to balance it. You need to balance it before we run or build any model. Got it? All of you understood the context of the imbalanced data here?
Yes, sir, clearly.
So now we need to do the class imbalance. See, class imbalance will occur. Class imbalance will be there in credit card fraud data, will be there in loan default data, will be there in customer churn data. Whatever data you are trying to classify, there will be some sort of thing. So when you look at
Cancer
this,
detection, sir.
pardon please.
Including cancer detection too.
Yeah, cancer detection, yes. Medical diagnostics, yes. Medical diagnostics like cancer prediction, COVID prediction, etc. So we can have all this imbalanced data. Now, when you have this imbalanced data, the right metrics would be imbalanced data. The metrics to be considered, the metrics to be considered are precision, recall or sensitivity is same, recall or sensitivity is same, recall or sensitivity is same, your F1 score, your area under ROC curve, or AUC, all these are the right metrics. So let us plot the ROC curve for this imbalance data also. Plot ROC curve, logit model, logit, comma, x underscore train df, comma, y. So if you look at the area under the score here, it is 0.83. It is 0.83. So the area under the score is 0.83, whereas in the earlier model we got 0.85. Here AUC is looking good, but sometimes before looking at AUC, we have to look at the imbalance thing also. This is the problem area. Okay, so basically, end of this, we have to understand that we have to balance our data. Okay, now let us install the library which is required for this. Pip install Imblearn. Pip install Imblearn. So this is a library within the Python environment, which is very easy to install, also very small library. Exclamation pip install Imblearn. Exclamation pip install Imblearn. This is the library we need to install for working with imbalanced data in Python. So this has all the required functions to deal with the imbalanced data. Now, while you are installing this package, let me just talk about the sampling technique. See, resampling techniques which are there for us to do are, first one, we have the undersampling. Undersampling means removing random records from the majority class. Okay, now there's a problem. This leads to loss of information. And this can be implemented only if there is very large data. When there is very large data, then we can implement the undersampling. But undersampling will lead to loss of information. The second one we generally use is oversampling. Now, oversampling is duplicate random records. From the minority class. That is we call oversampling. Now, there is a problem here. This leads to overfitting problem. Which is again a problem in data science. Too good to be true will be leading for overfitting problem. Now, this we implement when the data size is small. When the data size is smaller, these are the popular resampling techniques which are there. And we have also other techniques also. There are other techniques also which are there. Other sampling techniques which are statistically robust. that are statistically robust. One is the synthetic minority oversampling technique, also called as SMOTE. Similarly, we have random oversampling technique called ROSE. There's a ROSE is also there, which is a oversampling technique, which is there here. SMOTE is there, ROSE is there. We also have something like what we call random oversampler is ROSE. We also have something like Tomac links. Tomac links, which is again used undersampling. And we also have something called after Tomac links, which was by near miss. It's like KNN only, near miss. Near miss was also there, which are the sampling techniques that are statistically robust techniques. These are the statistically robust techniques which are there within the data science and machine learning for us to understand the various sampling methods. Okay. So all of you have installed the Imbalance. Yeah. So let us implement one by one these techniques using the Imbalance. Using the Imbalance, we can work on this technique. So from Imbalance dot undersampling import random undersampler. From Imbalance undersampling import random undersampler. Rus is equal to random undersampler. We have to set a random state is equal to 42. Replacement is equal to true. All right. Now, x underscore RUS, comma, y underscore RUS is equal to Rus dot fit underscore resample x underscore train df, comma, y. So we need both the dependent variable and independent variable when you're running this undersampling and oversampling process. So we have run the resampling of undersampling. From Imbalance undersampling import random undersampler, and we have undersample. Now let us understand what happened. Print y dot value underscore counts. Similarly, print y underscore RUS dot value underscore counts. So here the original data is 21,033 and 5674. Now the undersample data is 0 is also 5,674, 1 is also 5,674. So we have already what you call, see here, undersampled the data. Y underscore Rus has equated the majority class by randomly selecting the records and making it equivalent to the sample. Now we have 0 and 1 as 5674, 5674. Now let us run a basic model on this data. All of you have run the random sampler?
Yes, sir.
Now,
Sir, but how to decide which sampling or balancing technique to use?
that you will come to know. Once I explain all the 4 models, then you will be able to understand.
Okay, so we have to explore it by trying all the models.
Let us go by one. See, in some cases, what happens is, particularly when you are looking at publishing your data or research paper in a popular journal, then when there is a class imbalance, they will definitely ask you to balance the data. I have seen lot of papers getting rejected because the data is imbalanced. You have not enough records of the other class and all. Now, generally people try to replicate the data in Excel sheet using those multiple manual functions, and they might be unknowingly or unknowingly doing the undersampling or either oversampling. Now, when you can do that and replicate the data and equate it and do it, you'll get an output. But sometimes some journals will not accept that. They want you to use a statistically based robust method like SMOTE. SMOTE is a popular undersampling method which is widely used in academic research publishing. If your sample is undersampled, then most of the journals are accepting SMOTE based sampling methods. Okay, so SMOTE is popular in academic research. And there are other things which are developed for machine learning wise things. We have Tomac links, we have near miss. There are a lot of research is being done in machine learning also. So statistically robust techniques is what we have to use to support our research.
Okay, sir. Thank you for such a detailed answer, sir.
Yeah, sure. So let us look at what happens to our logistic regression model when we have undersampled the data. So logit underscore rust is equal to logit dot fit x underscore rust comma y underscore rust. Logit underscore rust dot core x underscore rust comma y underscore rust. So 75.70 is our accuracy. Based on the undersampling, 75.70 is our accuracy. So logit underscore rust underscore predict, pred is equal to logit underscore rust dot predict x underscore rust. Now print classification report of y underscore rust comma logit underscore rust underscore predict. Now you can see here our imbalanced data. Once you have undersampled, look at the overall accuracy 76%. Look at the precision, recall, and F1 score. They are also almost equivalent to both the classes. So random undersampling has given us the better model, where you can see here the overall accuracy is 0.76, and the precision, recall, and F1 score of both the classes are almost closer. Similarly, plot ROC curve logit comma x underscore rust comma y underscore rust. So the AUC curve is 0.83. There is not much of a change in the AUC. It is again 0.83. But if you can see the precision F1 recall of the minority of both the classes, they are closer to one another. So we have corrected to some extent the undersampling.
Yes, sir. Just to add, in this case, if you see the minority class accuracy precision has increased. Earlier,
Yeah.
it was less.
It was very less. Yes.
Yes.
Even
The minority class has got improvement.
Yes, its recall also has increased a lot. Okay, so the random undersampling is one method of doing this. So in random undersampling, we have equated the majority class to minority class. We have equated the majority class to minority class. That means we have randomly selected certain rows from our majority class, and then we have equated them with our minority class. The number of rows are equal, and then we built a model which is showing consistency on all parameters. Which is showing consistency on all parameters. Now, on this data, let us run oversampling method. On this data, let us run a oversampling method. From imbalance learn dot over underscore sampling, import random over sampler. Random over sampler. ROS is equal to random over sampler. Random underscore state is equal to 42. We are setting the seed. Now, X underscore ROS, comma, Y underscore ROS is equal to ROS dot fit underscore resample X underscore train df, comma, Y close bracket. So we have split the, we have done the oversampling. Now to check what actually happened, print Y dot value underscore counts, print Y underscore ROS dot value underscore counts. So now you can see here the minority class also has been duplicated. By duplicating the record, we have increased the minority sample from 5,674 to 21,033. We have increased it to 21,033. All right. So this is what it happens. Random oversampler. Now let us build a model on this. Logic underscore ROS is equal to logic dot fit X underscore ROS, comma, Y underscore ROS. Logic underscore ROS dot score X underscore ROS, comma, Y underscore ROS. So we have 75% accuracy, almost closer to 76% what we got here. It is also 76% we all got here. Now logic underscore ROS underscore predict is equal to logic underscore ROS dot predict X underscore ROS. Now print classification report of Y underscore ROS, comma, logic underscore ROS underscore predict. Here also random oversampling has almost given us the similar metric.
Sir, I have a question over here.
Yes, please.
Since we are oversampling it, and you said that due to oversampling, the minority class may overfit.
Yeah.
So how to check that whether it is overfitting or not? And if yes, then how to overcome it?
Yes. So for checking the overfitting problem, from you are asking for checking the overfitting problem. Checking
Yes,
the
sir.
overfitting problem can be done using cross-validation. It can be done using cross-validation or repeatedly checking the model, repeatedly running the model with same data. Okay. From sklearn dot model underscore selection import cross underscore val underscore score. Cross underscore val underscore score logit comma x underscore rows comma y underscore rows. Now, what is underfitting and what is overfitting? Underfitting means it is not able to reach the minimum threshold. Overfitting means on trained data, you get X accuracy. On repeated testing, the accuracy levels will fall drastically. Take for example, on trained data, you got an accuracy of 0.94 or 92. But when you repeatedly test the model using cross validation, your accuracies will fall to 70% or 60%. That we call it as overfitting. Here I have run the overfitting, what you call the model 5 times, and I got these scores. So the average score here is 0.75, which is closer to here. That means there is no overfitting here. Our original score is 0.76. See, our original score is 0.7595. The average of model running 5 times is also similar. Had it been gone to 50% or 40%, every time it runs, it gives you a different value, then we call it as a overfitting problem. Now, overfitting problem can be reduced by increasing the data. Here, if I run it on, let us say, cross val underscore score logit x underscore train df comma y. This is our original model, the imbalanced data. See, on the imbalanced data, initially we got how much accuracy? On the imbalanced data, we got good accuracy, right? On the imbalanced data, we got an accuracy
83.
of 83. Now, you can see here, it is also closer to 83 only. It is not overfitting here also. But the problem was the other metric, precision, recall, and F1 score is not overfitting. Even the imbalanced model is also not overfitting, because if you take the mean, it will be somewhere around 83%, right? So overfitting is not there in this problem. But if you have overfitting, generally we see overfitting in decision tree. So overfitting is more evident in tree-based models like decision tree. It mandatorily overfits. So how we do that? We reduce the depth of the tree by also giving an argument called max underscore depth. We can reduce the overfitting in the decision tree model. So decision tree model will obviously overfit, but we can overcome the overfitting by adding the depth of the tree as an argument in the model. By adding depth of the tree as an argument in the model, here we don't see any overfitting problem. Is it clear?
Yes, sir.
So the random undersampling, oversampling also will help us to overcome the overfitting problem. Okay. Now
Yes,
let us run the most popular one, the synthetic minority oversampling technique. Synthetic minority oversampling technique, also called as SMOTE. This is one of the popular technique which is used in healthcare and pharmaceutical diagnostics also, which is a approved technique by US FDA also. Okay. So SMOTE uses KNN methodology. KNN methodology, but not exactly the KNN. It uses the KNN methodology and creates synthetic data. The thing is, it creates synthetic data. In undersampling and oversampling, we are just either increasing the existing data or reducing the old data. We are not creating artificial data. SMOTE uses KNN methodology to create synthetic data or artificial data. It creates a artificial data, or we call it as synthetic data. So it uses a methodology of and it uses also the random number generator. It uses, SMOTE also uses random number generator for randomly selecting weights between 0 and 1. Typical random number generators select a default range of 0 to 1 until unless you specify the range to be greater than 10. So, for example, I have two data points. For example, there are two independent variables. Okay, it will. There are two independent variables, x1 and x2. Okay, the x1 values are 2400 and then 2500. These are the values of x1, and x2. There is a variable called 56, 68. Okay, so 2400, 2500, 56, and 68. Okay, so these are the data points we have, and we are trying to create a synthetic data or an artificial data from these two data points. We are assuming that there are two data points, and from these two data points, we are trying to create a random sample. Okay, a synthetic sample. A synthetic sample has to be created using these two data points. Okay, so we have these two. Now, what it will do is it chooses a random number. It chooses a random number between 0 and 1. Let us say here the random number is 0.60. It randomly chooses a random number called 0.60. Then it will start calculating. 2500 plus 0.60 of 2400 minus 2500. So it will use this, it will calculate a new value. So 2500 plus 0.60 of this, let's make this as 68, and then this is 56. Okay, and it will also use for the second variable the next value, which is 56 plus 0.60 into 68 minus 56. So if you do this calculation, I think you will get minus 100 into 0.60 is 60. It will become 2560. Okay, minus max. So it will become 2440. Right. This will become 9, right? 7 into 42. That means this will become 60.2. So you will get a value between the range. You will get the value, the synthetic sample will be between the range only. It will not create an outlier or it will not create an outside value. So the new synthetic sample will be within the range of the observations. The new synthetic sample in this case, the new synthetic sample in this case is 2440, comma 60.2 are in between the range. So it is not going to create something out of the range. It will create the variable, the synthetic data will be created within the range. Within the range, it will create. So the synthetic minority sampling technique is a statistically proven technique wherein it creates synthetic data or artificial data using a random generator as a weight, and it does the weighted average calculation, weighted difference calculation, or weighted addition calculation to create new data points. It will create new data points which will fall within the range, which are not out of the range. That is the biggest advantage of SMOTE. This is the biggest advantage of SMOTE. So whatever sample it will create within the data ranges. It will not go outside the data range. So that is why SMOTE is considered to be a very good sampling technique which keeps the data within the range.
Sir, can you tell us about the randomness that uses, sir? Does it consider uniformly normal, or it's a different kind of randomness that it considers?
No, uniformly normal. The one which you have in Excel, right? Random number generator.
Right.
Same random number generator is there in Python also. np.random. You have to just give the range. By default, the range is 0 and 1. If you go into Excel, by default, the range is 0 and 1, right? Within the 0 and 1, it will create a random number.
Okay.
So same type of random number generator is used in here also. np.random. And by default, the range is 0 to 1. If you want, you can increase the range also, but by default, the range will be 0 to 1. So this is how SMOTE creates synthetic data. This is how the SMOTE creates synthetic data, and SMOTE is an oversampling methodology. SMOTE is an oversampling methodology, not a undersampling methodology. It's a oversampling methodology. And it follows a similar methodology similar to k-nearest neighbors, but instead of distance, in KNN we calculate the distance, right? The Euclidean distance. Here it's a different scenario. It is not the distance, it is the weighted addition or weighted subtraction based on the random weight. Is it clear?
Yes, sir.
Yeah. So let us run this from IMB learn oversampling import SMOTE. Import SMOTE. SMOTE is equal to SMOTE. So x underscore SMOTE, comma y underscore SMOTE is equal to SMOTE dot fit underscore resample x underscore train df, comma y. So we have created a SMOTE value here. So print y dot value underscore count, print y underscore SMOTE dot value underscore counts. So see, it has also created a oversampling 21033, 21033. So it also created the oversampling only. It equated with the what you call the majority class, but in the minority class, it uses the synthetic data or artificial data which is created using the SMOTE mechanism is not there. It did not duplicate the columns here, rows here. It has created a new synthetic or artificial data. It has created a new synthetic or artificial data, not duplication of data. That is the difference between SMOTE and
Sir,
your,
sir, this one also must be working on the numerical data types only.
yes, for this also we need to, because it has to calculate this, right? The data has to be numerical format.
Right, sir.
The data has to be numerical format because it has to do weighted addition or weighted subtraction.
Sir, then what about the object or string type or categorical data type? Even if we get the dummy values, their values are generally integers. So,
Okay.
So when the SMOTE will run, it will also it will give only integer values.
No, see, what it will do is when it is running on categorical data, it's a different process it follows. One
Okay.
second. Imbalance mode is a different one. So for object data, see here, when it is string, sorry, I'm going from SMOTE to SMOTE and see here. All right. But computer is stuck actually. Yeah. So when specifically string, when string specify the class targeted by the number of samples in that will be equalized. It can be resample only the minority class, not minority, not majority, resample all classes. Resample all classes and auto equivalent to not majority. So by default it is all. That means it will resample all classes. Okay.
Yes, sir. But if it resamples all the classes, which is already imbalanced, don't you feel that the actual proportion of the class will change?
Yes, it is changing now. The actual proportion of the class has changed already, right? It has
Yes.
become more sample, 21,000, 27,000. Na?
Yes, sir. Yes, sir.
So,
Got it, sir. Got it, sir.
but the thing is, how it behaves, the synthetic data behaves in the algorithm is important.
Yes, sir.
So that we will know once we run the algorithm. Logit SMOTE is equal to logit dot fit x underscore SMOTE comma y underscore SMOTE. Logit SMOTE dot score x underscore SMOTE comma y underscore SMOTE. 76%. It has slightly increased the accuracy. It has slightly increased the accuracy. But what about the other metric? Logit SMOTE predict is equal to logit SMOTE dot predict x underscore SMOTE. Print classification report of y underscore SMOTE, comma, logit SMOTE predict. Now you can see all the classes overall accuracy slightly has increased, and then you have the precision, recall, everything coming closer. And I think cross validation also will give you the same type of accuracy. Cross val score logit x underscore SMOTE, comma, y underscore SMOTE. See, I think it is also giving you the same type of classification accuracy, which you can see on the model-based accuracy also.
Yes, sir.
So SMOTE is an oversampling technique which is statistically accepted in, we use SMOTE in the credit card fraud data points and all. The regulators have allowed the SMOTE to be used. I think in pharmaceutical studies also and medical diagnostics also, SMOTE is being widely used. SMOTE also is being widely used. Now this is a special type of imbalance technique which we have special type of oversampling technique we have used. If you are looking at a special type of undersampling technique, we have a technique called near miss. We have a technique called near miss, which is a typical undersampling technique. So, which is a typical undersampling technique, or let us run Tomek links. Undersampling Tomek links. So these are pairs of very close instances, but on opposite classes. So Tomek links identifies the pairs of very close instances, but on opposite classes. It removes such instances of majority class. Such instances of majority class, and increases the space between, classes in classification model. Now, this type of paired base we see regularly. Now, let us say I have an example data like this. Example. Now, the age of the customer is 25. The income of the customer is 12,000. The location of the customer is city. The what you call the education qualification of the customer is BCom, and he has made a purchase. Yes. Now, same 25-year-old person, same 12,000 thing, same city, same BCom, purchase is no. So you will see these instances, right? We see in our data, we have exactly same independent features, but the dependent variable changes, right? I think most of you are familiar with this type of scenario, right? When you do surveys in your classrooms or anything, the sample size will have same age, they come from similar family background, they're all city, the qualifications will be same, but there will be change in the dependent variable preferences, yes or no. So Tomek links are pairs of these very close instances, but on the opposite classes. Here I am given exact. It can also be like this. Age might be 24, income might be 13,000. Instead of BCom, he can be BA. But basically what you call undergraduate category only, right? So we will see these type of situations in our data. When you have such type of situations, Tomek links is the best option. When you have such situations where your sampling, where your independent variables are very close, but the final dependent variables changes, we can use this Tomek link. So Tomek is equal to random undersampler sampling strategy is equal to majority. So by altering the sampling strategy to majority in undersampling, we can implement the Tomek undersampling method. By just giving a sampling strategy in random undersample, we can do the Tomek. So X underscore Tomek, comma, Y underscore Tomek is equal to Tomek dot fit underscore resample X underscore train df, comma, Y. So we have created the Tomek. So print Y dot value underscore count, print Y underscore Tomek dot value underscore counts. See here, it has undersampled to 5,674 by removing the closed instances data, which will fall on the other side. It's an undersampling technique which is used to if you have very close pairs of data on in your data structure. So the Tomek links are also used when you have these closed instances of data where independent variables all look similar but fall onto the opposite side of the class. Now let us build a logic Tomek model and see the interpretation. Logic Tomek is equal to logic dot fit X underscore Tomek, comma, Y underscore Tomek. Logic Tomek dot score X underscore Tomek, comma, Y underscore Tomek. So 76% slight increase in accuracy, not much, but very slight increase in accuracy. Logic Tomek predict is equal to logic Tomek dot predict X underscore Tomek. Print classification report Y underscore Tomek, comma, logic Tomek predict. Here also see the precision, recall, and reference for all are closer to one another. They are very close to one another. So you can see the Tomek links also a very undersampling technique, which is also used in data science or machine learning purpose. Now, the question comes when to use what? When to use the what thing? You have to be little bit getting confused. So, SMOTE versus Tomek. Let me see if I can find a straight differentiator between SMOTE and Tomek links. In fact, there are new methodology where we can run both oversample as well as undersample.
So how does it make a sense? You said that we can use oversampler and undersampler in the same.
Yeah, and the same. Yeah. So combination of SMOTE and Tomek link undersampling. So SMOTE Tomek class. It is called SMOTE Tomek class, which is both versions. You can undersample as well as oversampler. I think in Imbalance only we have this Tomek thing. So combinations are there, SMOTE plus Tomek link. So when we can use is so when you use SMOTE plus Tomek, first SMOTE will be applied to oversample the minority class to a balanced distribution. Then Tomek links from the majority classes are identified and removed. So the combination was shown to provide a reduction in false negatives. It has helped in reducing the false negative. So you can see here, SMOTE cum plus Tomek.
आप कुछ इंस्टॉल नहीं कर सकते हो ना, आपका अकाउंट ब्लॉक किया गया है ना.
SMOTE plus Tomek.
कुछ नहीं, बाकी पढ़ाई करो. बाद में करूंगा उसको, और बाकी अपना काम करो, दूसरा कुछ कर लो.
So here, the combination was shown to provide a reduction in false negatives at the cost of an increase in false positives for a binary classification task. So if you are looking at these various things, we also need to look at the what you call the confusion matrix in detail. That way it will help you to do it. SMOTE plus Tomek will reduce the false negatives at the expense of false positives. Similarly, if you look at so SMOTE plus edited nearest neighbors, this is also can be done. They say ENN is more aggressive at downsampling the majority class than Tomek link, providing more in-depth cleaning. So if you look at SMOTE and the SMOTE plus edited neighbors, it is more aggressive than Tomek in removing the downsampling the majority class. So there are research papers we can see where we can see whether the false negatives or false positives will affect or not. So on what exactly it affects. So if you are looking at SMOTE impact on false positives and false negative. So basically, SMOTE will help you to, here it is given. Using SMOTE, we can tweak the model to reduce the false negative at the cost of increasing the false positive. So SMOTE will reduce the false negatives and increase the false positives. So if you think your false negatives are becoming too much of a problem, then use SMOTE. SMOTE is used when you want to reduce the false negatives at the expense of false positives. So it is very clearly given here. So I'll paste this here to understand when to use SMOTE. SMOTE, TOMEC also will do that, right? In our data, which is more problematic. False negatives are more problematic, right? Compared to false positives. So if you look at our confusion matrix, what is more problematic? The problematic is false negatives, type 2 error, right? So when you look at our data science, we are more bothered about false negatives, which are your type 2 error. Type 2 error is more dangerous than type 1 error. Type 2 error is more dangerous than type 1 error. So when you want to reduce the false negatives or type 2 error, you have to use SMOTE. So when you look at your confusion matrix, and if you see false negatives are creating problems, to reduce them, you can use SMOTE.
Sir, can you repeat, sir?
See here,
Please.
I have written it here. Using SMOTE, we can tweak the model to reduce the false negative at the cost of increasing the false positive. And the same thing can happen with SMOTE plus TOMEC. Because false negatives are problem in our data, we can reduce the false negatives. They are more dangerous. False negatives are your type 2 error, which are more dangerous than your type 1 error. So, if you want to reduce your type 2 error or false negative, then we have to use SMOTE methodology to increase the, it will increase the false positives, but false positives are less dangerous compared to false negatives. Okay.
Yes, sir.
So similarly, if you are looking at random oversampling versus random undersampling. Random oversampling and random undersampling. There is actually a differentiating thing, a table which will help us to do. So imbalanced data is one of the most researched data. So here. So this study has found out for logistic regression, linear discriminant and random forest, undersampling Rust is preferred. For oversampling, ROS, SMOTE is preferred. For hybrid, SMOTE plus TOMEC and SMOTE plus ENN. So you can see here IST's instant hardness threshold. So there are some studies which are done to specify which sampling methodology to use for different algorithms. For random forest, I think SMOTE plus TOMEC is a very good option. Logistic regression, undersampling and oversampling, I think Rust and ROS will be help to do that. So we have these research papers where there are a lot of studies being done for different classifiers and methodologies. Or let me check if I can get a good classification table. So oversampling is comparatively, yes, you're right, sir. Murthy sir, you're absolutely right. Yes. So comparatively, oversampling is better than undersampling. From based on certain areas of studies, it is better to oversample than undersample. But there are a lot of research papers. But nowadays they are using the combined method of SMOTE plus TOMEC. You can also, friends, do research on this area of empirical study of data, running of both all these techniques, and you can publish a paper on the behavior of the various things. So you can look at the, basically you have to look at the confusion matrix. For when you are doing this type of study, focusing on confusion matrix will be a better option, which I will show you right now how to focus on the confusion matrix of different things. Then we will be able to study the actual impact. Okay. Take for example PD dot crosstab y underscore SMOTE comma y logic SMOTE predict. So this is our SMOTE based prediction. 4469 is our here what is positive and negative? Is 0 positive or 1 positive here? In our case, 0 is negative and 1 is positive. So for us, true negative is 16,564 and false positive is 4469. False negative is 5377 and true positive is 15656. Okay, so this is for SMOTE. But if you do our actual data, CD dot crosstab y comma logic model we have predicted it, right? Logic imbalance predict. Imbalance predict. Yeah. Imbalance predict is the name I have given there. So this will be imbalance predict. So for imbalanced data, 1115 is the false positive and false negative is 3300. And 0 and 1, minority and majority are, because this is an imbalanced class data. So I think more of the ones are being, more of zeros are being predicted correctly. So y dot value underscore counts. See, out of 21,033 zeros, 19,918 are being predicted correctly. And out of 5,674 ones, only 2,374 are being predicted. So if you look at the difference, 3,300 of the ones are wrongly being predicted, 1,115 zero. So this is what happens with imbalanced data. Wrong predictions of the positive class is higher than the wrong predictions of the negative class. In our case, people who did not take vaccine are negative, and people who have taken vaccine is positive. So if you can see here the amount of thing here, I think there are equal amounts of thing is being predicted wrong. So FP sensitivity and specificity is okay here. There's not much difference when you SMOTE do the oversampling and do it. Whereas when you look at the actual data, the problem lies in the minority class, right? You understood the relevance of balancing the data here?
Yes, sir.
So this is what happens. So medical diagnostics, this is very dangerous. For medical diagnostics, this is very, very dangerous. So you have to be very careful when you're looking at this type of data. Okay. And most of the studies are saying combination of SMOTE plus STOMACH is better, or SMOTE plus nearest neighbor is better. Okay. So that is how we have to model the data. All right.
Yes, sir.
Now, for imbalanced data, if you don't want to balance, then tree-based models like decision tree work better. Decision tree or your ensemble methods. Your ensemble methods like random forest, they're all tree-based models, right? Random forest and gradient boosting machines, which are your tree-based models, have a better performance. So these set of algorithms have better performance, because what happens is tree-based models use rule-based predictions. Rule-based predictions, which means from the tree, if then else rules are created and are used for prediction. So that is the reason why for imbalanced data, tree-based models are better. To prove this point, let us run a tree-based model from sklearn dot tree import decision tree classifier. Tree is equal to decision tree classifier. Tree model is equal to tree dot fit x underscore train df comma y. Tree model dot score x underscore train df comma y. Oh, overfitting. Okay. By default, the decision trees will overfit. So to reduce the overfitting, we have to specify max underscore depth. Max underscore depth is 8. Randomly, I am selecting 8 and I am fitting the model. With 8 depth tree, our accuracy is 85.16. I am increasing it to 12. 90.36. This looks good. A tree model, because by default decision tree will be overfitting. To reduce the overfitting, you have to specify the max depth of the tree, or how many layers have to be there in the tree. Now we got with the 12 depth. max depth of the tree is 12, we got an accuracy of 90.36, and tree predict is equal to tree model dot predict x underscore train df. Print classification report of y comma tree predict. Now you can see here the tree model precision is okay, F1 score is okay, but recall is less. But compared to logistic regression model, the recall is less. The recall is less, but the other two metrics seem to be okay. The other metrics seem to be okay, and the difference is also a little bit higher. Compared to logistic regression, for an imbalanced data, tree model have certain better performance. But here the recall is again a problem. Recall metric is nothing but your sensitivity. What is sensitivity? True positive divided by true positive plus false negative. So that is creating a problem, but overall metrics are good. But this is not as worst as your simple logistic regression, which I have built on the model. See here, this is the oversample. Imbalanced data. See, so recall is 42, 52, 68, and then here we can see here recall and considerably far better than your normal logistic regression model. But recall is still a problem. So recall is still a problem, which is basically true positives are wrongly predicted. So that is what we can see here. But if you run a gradient boosting regressor from sklearn.ensemble, import gradient boosting classifier. GBM is equal to gradient boosting classifier n underscore estimators is equal to 1000. GBM model is equal to GBM dot fit x underscore train df comma y. So I'm building a gradient model because that is comparatively better than random forest. So it ran for me GBM model dot score x underscore train df comma y. Score is 87.34. 87.34, which is a comparatively better than our logistic regression. GBM predict is equal to GBM model dot predict x underscore train df. Print classification report y comma GBM predict. So this is somewhat closer. Recall is again problem for this thing. Rest of the F1 score is also very less. So GBM is not able to. It's only predicting 87. But if we increase it to estimators to 3000, will it work? So if you want to use a better model than, if you don't want to balance the data and then you want to use, then the tree-based models have a comparatively better performance than the basic models like logistic regression. So gradient boosting machine is supposed to be the better model. Still running. Okay, so let us see what we have. Yeah, it has run 89. Now it has slightly improved, 90% accuracy with recall of 64, F1 score of 72, and precision of 84 for the minority class. So sort of imbalance is better. Okay, so you can see here the tree-based models have a better performance compared to the basic logistic regression model. We can also use support vector machines. So the SVC also has an inbuilt feature. If you look at the support vector classifier, you can do sampling also in SVC. SVC sklearn, since SVC is widely used in image processing, image processing. Here we have a function called weight size variables class weight. See here, class weight is equal to none. So you can say class weight is equal to balance. So class weight can be converted to balance. So in support vector machines, will help you to run with class weight is equal to balance also. So class weight balance will help you to fit a model in SVC with a balanced class. So because SVC is widely used in what you call support vectors are used in image classification, you can simply run it by just giving the class underscore weight is equal to balance. If we say balance, it will balance the data and then it will fit the model. Got it? So SVC has an inbuilt function. Class weight, you can give an argument as balanced, then it will balance the data. uses the values of y to automatically adjust weight to inversely proportional to class frequencies in the input data. So this is the formula it uses to balance the data. So if you want, we can simply run it from sklearn dot svm import svc support vector classifier. svc is equal to svc class underscore weight is equal to balanced. Class underscore weight is equal to balanced. And then comma probability is equal to true. SVC model is equal to SVC dot fit x underscore train df comma y. So support vector machines have the ability to balance the class weight incorporated into the model. It's still running. So SVC support vector machines uses vector mathematics. It transforms the data. The kernel is very important here. It transforms the data from one dimension to other. Radial basis function is one of the popular kernel and default kernel in SVC. Radial bias function. RBF kernel is a popular kernel. I think exponential to the minus gamma into the formula for radial bias, I forgot. RBF. RBF.
Radial basis function.
Radial basis function. The formula is this: exponential to the power of minus d into gamma. D is nothing but gamma into xi comma xj square by 2l square. L is the length of the kernel. So this is the default function within the SVC in Python. In SVC in Python, it uses the radial bias RBF as the default radial bias function. The kernel is equal to RBF. The kernel trick is very important in SVM. The kernel trick is very important here. By default, the kernel trick is RBF. RBF is better than the other kernel trick, which is your linear and logistic kernel. So based on this methodology also, we can, using a support vector machine for image processing, you can balance the classes and do it. Taking a lot of time to compute, but still. taking a lot of time. Let's see why it is taking so much of time. So any doubts in imbalance data, participants? Okay, so it takes a lot of time to run SVC. So while it runs, let us browse through the last part of our workshop today. The feature selection. So feature selection method or selecting variables will reduce overfitting, will make models run easily, and will also help us reduce training time. The model training time and all those things, feature space can be reduced. Using this feature selection method. Now, in feature selection method, so in feature selection method, what we do is generally we used to select based on multicollinearity. Initially, we used to select basis on multicollinearity or with variance inflation factor or manual selection or through variable importance from decision tree, random forest, and gradient boosting machine. So we used to do it like this, which is how we used to select the variable. But now Python has come up with a lot of other methods. So one of the important method is in sklearn Python, feature selection based on, so if you are looking at feature selection, so there are different methods. One of the most important method is select k-best. So select k-best is a method which is widely used, and in select k-best method, there are many methods. You can see, you can use an ANOVA based method. You can also use a mutual information method. You can use a chi-square method. You can use the F regression, mutual info regression, select percentile based on false positive rate. So you can select variables using these methods. So when you use this select K method, you have to specify the function which you want to do, and you also need to specify how many of the top features you want. By default is top 10 features. You can specify the number of features you want also. So it ran for me ultimately. So HPC model dot score x underscore train df comma y. So it has run. So let us see how it will give. I think it will give a less score because this data is not suitable for this thing. So for select based on your thing, you can select important variables or features using the select k-best method in Python. The select k-best method will help you to identify the best variables, and once you get the new set of variables, you can use them and use this, understand those variables and improve your model performance. That is what happens in select k-best method. So you can select k-best method based on ANOVA, based on chi-square, based on false positive rate, based on false discovery rate. So you can see there are many methods which you can use within the select k-best. And you can specify how many features you want, how many variables you want. If you don't specify, default is 10 variables. Default is 10 variables. So you can use this select feature selection method when you are dealing with large scale data points. When you are dealing with large scale data points, particularly when you are dealing with many variables, say if you are dealing with more than 50 variables, I would always suggest use select k-best to reduce the number of variables. If your variable is more than 70 or 100, definitely you have to use select k-best. Definitely you have to use select k-best method for this way. So without doing that, we can't build a proper model. So SVC predict is equal to SVC model dot predict x underscore train ds. And then we will also do this one. So train classification report until it runs, we can't fill it. And then we'll see it. So going back to the feature selection model, select k-best is one of the most used method in machine learning and data science, which I have seen when you have too many variables in your data. So if you want to reduce the variables, if you want to reduce the model complexity, if you want to reduce the model building time, then select k-best method is a better method of selecting the features rather than the traditional of multi-collinearity or doing. There are methods also. Variable importance methods are also good. Not that tree-based models are bad. The variable importance method given by tree-based models is also a very good methodology. I have also seen them. They are also being performed well, particularly random forest-based variable selection. Random forest-based variable selection methodology is a very good methodology I have seen, which is being practically used to reduce the number of variables. So, but if you want to use more than that, you can go using these methods. Y, SVC predict. So classification report, you can see here, overall accuracy is 79%. Precision is less, but recall and F4 are okay. Recall and F1 score compared to the event, they're very low of them, not okay. They are very less. They are very less. So SVC based for this data is not a better model. SVC based balancing is not a better model. Okay. So I will show you a couple of the feature selection methods and how to implement them in Python. From sklearn.preprocessing, import, sklearn.feature selection, import select k-best, select k-best, epsilon dot pre-processing, import, select k-best. So select k-best, I will use chi2 first. Okay. X underscore new is equal to select k-best in bracket chi2. Okay, we have to import chi2 also, comma chi2. Chi2, let it be 10 variables. Okay. Dot fit underscore transform x underscore string dx, comma y. So x underscore new dot shape. See, it has reduced the variable to 10 variables. It has reduced it to 10 variables based on the chi-square test. Based on the chi-square test, it has reduced it to the top 10 variables. Now, we can now use this data, logic underscore k-best underscore chi is equal to logic dot fit x underscore new comma y. Logic k-best chi dot score x underscore new comma y. See, 83%. The model accuracy has drastically increased. Let us do the logic k-best underscore chi underscore predict is equal to logic k-best underscore chi dot predict x underscore new. Print classification report of y comma k-best chi predict. So the recall and export are there. Imbalance is still a problem. Imbalance is still a problem even if you select the variable. So we have to first deal with the imbalanced data, and then from the imbalanced data we can select the best k variables. So feature selection on imbalanced data has to be done post the imbalance is solved. Post the data has been balanced, then you have to do it. Now we have the imbalance also here, x underscore SMOTE and y underscore SMOTE. I think we can do that on this one. So let us say SMOTE underscore new is equal to select k-best chi2 dot fit underscore transform x underscore SMOTE comma y underscore SMOTE. Now logic underscore SMOTE underscore chi is equal to logic dot fit SMOTE underscore new comma y underscore SMOTE. Logic SMOTE underscore chi dot core SMOTE underscore new comma y underscore SMOTE. 75% accuracy. Okay, then logic underscore SMOTE underscore predict is equal to logic SMOTE underscore chi dot predict SMOTE underscore new. Print classification report y underscore SMOTE comma logic SMOTE predict. Now you can see the recall, F1 score, everything is good. So after imbalance data, you can select the variable, and based on the variables, the accuracy levels are slightly increasing, not much, but there is a slight increase in accuracy. We can increase the accuracy further, and these are very stable models. Using these feature selection methods, you can select the variables, reduce the model complexity, and also run the models faster with stable outputs. So the methods are many in K-test, select K-test method. Apart from the normal methods which we do, we generally use methods like manual selection, variable importance, and all will be there. In feature selection, if you have based on ANOVA, you have one based on chi-square, you have one based on false positive rate. So let us see the FPR rate also. One last model we will fill, and then I'll take your doubt whether FPR will be an issue or not. Select FPR. Select FPR will be interesting or what? Select FPR. So select FPR, false positive rate. And the core functions is again chi2. So I'll run a model with select FPR. Variable selection using false positive rate. So SMOTE underscore FPR is equal to select FPR. We'll go with the chi2 only. Dot it underscore transform x underscore SMOTE comma y underscore SMOTE. So we have built this model. Logic underscore SMOTE underscore FPR is equal to logic dot with SMOTE underscore FPR comma y underscore SMOTE. Logic SMOTE underscore FPR dot score SMOTE FPR comma y underscore SMOTE. 70-60. The accuracy has further increased. The accuracy has further increased. So logic SMOTE FPR underscore predict is equal to logic SMOTE underscore FPR dot predict SMOTE underscore new or SMOTE underscore FPR. Print classification report y underscore SMOTE comma logic SMOTE FPR predict. This also slight increase, 77% accuracy increase by reducing the variable. So there will be changes in the output by selecting these features or variables. Your accuracies will increase. And there are a lot of feature selection methods which are there, which can be implemented using these models. So these are very interesting things which are happening in Python, where there are a lot of automation being done to reduce the model complexity. So in this way, you can look at the imbalance, you can look at the feature selection variables, you can also create models and then select from the model. So there is one more thing called K-based selection from model. You can build a model and then select from model is also there. So So select from model is also there, which will help us to identify the model based on the model. So say you have built all the model and see which are the important variables. And this is your select from model. This is also a very interesting feature, which is there if you want to select from the model itself. Okay, so once you select the model and then you will transform the data, you will get the number of variables based on the model. So in select from model, you can select variables and max underscore features integer you can give, how many features you want to give. You can give that integer features and then it will give you the select from model also. So we can also use this select from model to select the important variables based on the pre-built model. Pre-built models we can use. So we have built a pre-built model, I think on gradient boosting, right? We have done a gradient boosting classifier with 90% accuracy. So shall we select this model from gradient boosting classifier? So select from model, you can select the gradient boosting method like this. Select from model, the estimator has to be given, and then it will select the variables based on the estimator. So selector is equal to select from model, estimator is equal to gradient boosting classifier dot fit underscore dot fit x underscore SMOTE comma y underscore SMOTE. So let me just this thing down. Here we'll give n underscore estimator equal to we'll give 1000 only this time. We'll not give many, we'll give 1000. So we can also give max underscore feature. Max underscore features is equal to 10. We want only top 10 features based on the gradient boosting classifier. So we will get the selector data. So once you have run this thing, you get the new data from the model, gradient boosting model, and then it will pick up the top 10 features in the model, and then it uses them to build a model. So you can also select the features from the existing model, like how you told, decision tree and all have variable importances, which will give you important features. So that way you can get the important features. So this is running to, and it will give us the top 10 variables based on the gradient boosting classifier, and we can select those 10 variables and build our final model. So select k-based is there, select from the model is there. You can select variable importance from tree-based model. You can do manual selection of variables. So there are different ways of selecting the features. If you want to select the features using statistical methodologies, then you have to use these models. So these are the feature selection models which are there in Python, which can be used in selecting the important features when you build your final model. All these methods are available in all the machine learning workbenches and cloud computing workbenches, where we can easily use them for machine learning and doing advanced analysis. So these are the feature selection methods which are there in Python, which are the addition from the last two versions of sklearn. where they have introduced these statistical based methods to make more effective the machine learning model, to reduce the overfitting, to reduce the time, to reduce the complexity of the model. We must have these sort of feature selection methods. So these are the methods which are available. So selector has already run. So x1 underscore new is equal to selector dot transform x underscore SMOTE. So x1 underscore new dot shape. So we have only 7 variables. Oh, size of the things also have increased. Oh, I think I made some mistake somewhere. It has doubled the data. So there is some error here. Select from model. There is an error here which I made. Select from model. Something happened. Or transform also is correct, but it doubled the data. So there is this error which is happening. Let me see what it has done. Let us see what are the features we gave as important features. Selector dot get param x1 underscore new dot get underscore features, not what to do. It is not giving us the complete thing, and it has doubled the data. So there is an issue here. Select from model. I think it is running the 2 times and it is giving the double the data. Why it is doubling the data, I don't understand. Okay, so this doesn't make sense because 42,056. It doubled the data, 21,033 to 42,066. Okay, so okay, I think it has created both the classes. Okay, it's correct only. SMOTE will be 42,066 only, right? So it is right only. So x1 underscore new dot head. So pd dot data frame is correct only. So because SMOTE has double the data, right? Column is equal to x underscore underscore SMOTE dot columns. So feature names, it identified top 7 variables only. But what are those 7 names? We can't. So I think best select method. Oh, I think I've corrupted the data in the beginning, so that's why it is not giving us the variable name. But you can reduce the shape like this using this select from model also. So these are the methods which are there, which I wanted to discuss today. The feature selection method, the imbalanced data, and your basic what you call imputation method, KNN imputer. Okay. So from my end, this is what I wanted to discuss with you guys. So if you have any doubts, I can answer them now.
No questions from my end, sir. There is so much to learn from you. I mean,
Thank you, sir. Thank you very
again,
much.
you have explored or demonstrated so many new things which are there and which I do not know. I mean,
Yeah, it's a constant learning process, sir. Because even I have been learning a lot of things because a lot of advances are happening in the data science field. So it's a constant learning from from everybody's side.
and the most important thing is that I'm listening to you after so many years, and today also I found the same passion in you.
Thank you, sir. Thank you very much.
Thank you, sir.
I have sent the file in the chat window. You can download the file from there, participants. Okay, so if you have any doubts, you can ask me now. And I will share the video also. Just can you drop your emails in the chat window, please? If you can drop your emails, I think Nihar sir I have already. If you can drop your email.